Okay, Assalamualaikum to our lecturer Encik Muhammad Sahari bin Muhammad Fauzi. Today we are group 5 going to present about a dual combustion engine and the auto cycle. Okay, I gonna present first. My name is Wan Muhammad Irfan Khalis bin Wan Muhammad Hafiz. My metric number is 01 DKP23F 1038. Okay, let me start first with a dual combustion engine. A dual combustion engine, often called a dual fuel engine, is an internal combustion engine that can run on two different types of fuel simultaneously or separately. In many cases, it uses a primary fuel such as natural gas and secondary fuel such as diesel to ignite the combustion process. In a typical setup, the primary fuel like natural gas is mixed with air and introduced into the cylinder. A small amount of diesel is then injected to ignite this air fuel mixture, allowing the engine to benefit from the efficiency and cleaner combustion properties of gas while using the diesel as a pilot to start combustion. Dual combustion engines are widely used in large applications like marine vessels, power generators, and industrial engines, where flexibility, fuel efficiency, and lower emission are beneficial. It can refer to engines that first we have use two types of fuel. These engines are designed to run on two types of fuel such as diesel and natural gas to improve efficiency, reduce emissions, or lower fuel costs. The engine can switch between a fuel or use both simultaneously. Common in heavy-duty engines, this approach leverages the strength of each fuel type, like the high energy density of diesel and the cleaner combustion of natural gas. Okay, second, we have a dual combustion cycle. Some engines operate with two different combustion cycles within one engine, combining elements of both diesel and auto cycle as in the dual or mixed cycle engine. This approach aims to increase thermodynamic efficiency and optimize power output.
Hi, my name is Roshan Anarakinandakuma. My normal metric is 01 DKP23F 1039. Today I'm going to explain about auto cycle. The auto cycle is a thermodynamic model that describes the four-stroke process in many gasoline-powered engines, detailing how fuel is converted into a mechanical engine. This cycle consists of four main stages, repeat continuously to generate power. First, the isentropic adiabatic compression stage compresses the air-fuel mixture within the cylinder as the piston moves upwards, causing the temperature and pressure to increase without any heat addition phase, where the spark plug ignites the compression mixture at the top of the cylinder. The combustion rapidly increases the pressure and temperature within the confined volume, setting the stage for the next stage in the isentropic adiabatic expansion or power stroke. The high pressure gas pushes the piston downwards, transferring energy to the crankshaft and producing mechanical work to power the vehicle. Finally, in the constant volume heat rejection phase, the exhaust valve opens and the piston moves upwards to expel the combustion gases, reducing pressure and temperature. This exhaust stroke clears the cylinder of spent gases, preparing it to start the cycle again with a fresh intake of air-fuel mixture. Together, these stages describe the idealized operation of many internal combustion engines, forming the basis for efficient power generation in automotive design. Next, I'll explain about isentropic adiabatic compression. When the intake valve closes, it traps the air-fuel mixture in the cylinder, marking the start of the compression stroke. As the piston moves upwards, it compresses the gas mixture, significantly raising its pressure and temperature. This process is adiabatic, meaning no heat is transferred to or from the surrounding. So the increase in temperature and pressure is solely due to the work done by the piston compressing the gas. The compression stage is crucial because a higher pressure and temperature improve the efficiency of the upcoming combustion. However, the compression ratio must be carefully controlled to prevent knocking, which is premature ignition caused by excessive heat and pressure. This isentropic compression phase prepares the mixture for an efficient and powerful combustion in the next stage, enhancing the overall performance of the engine. Next is constant volume heat addition, ignition and combustion. At the end of the compression stroke, the spark plug ignites this highly compressed air fuel mixture, triggering rapid combustion. This combustion phase occurs almost instantaneously, causing a sudden and dramatic increase in both temperature and pressure within the cylinder. Because of the combustion happens so quickly, the piston remains nearly stationary at the top dead center (TDC). So the process effectively takes place at a constant volume. In the brief moment, the energy releases from the burning fuel adds a large amount of heat to the system, which further drives up the pressure without changing the volume. This sharp rise in pressure creates a potential energy needed to drive the piston downwards in the next stage, generating the force that powers the engine. This phase often called the constant volume heat addition.
Assalamualaikum. My name is Muhammad Faikal bin Ramli. My track number 01 DKP 23F1041. Alright. Next, I will present about the process of 4 main stage. Stage 2, constant volume heat addition, ignition and combustion. At the end of the compression stroke, a spark plug ignites the air fuel mixture. The rapid combustion happens almost instantly, causing the temperature and pressure to rise sharply while the volume remains nearly constant. Since combustion is so fast, the piston has not moving significantly. So the process happens at the process volume. The energy released from combustion adds heat to the system, increasing pressure without changing volume. Then stage 3, isentropic adiabatic expansion. The high pressure gases expand, pushing the piston down with force, which drives the crankshaft and provides power to the engine. This is another adiabatic process where the gas expands without heat exchange. The expanding gas does work on the piston, converting thermal energy to mechanical work, which in turn power the vehicle. Alright, the last stage is constant volume heat rejection or exhaust stroke. After the expansion, the exhaust valve will open, allowing the burning gas to escape. This reduces pressure in the cylinder at nearly constant volume, completing the cycle. The exhaust gases are released, removing heat from the system. This is final step, completes the cycle by bringing the system back to its original stage, ready for the next intake stroke. Alright, the last one is efficiency of the Otto cycle. The efficiency of the Otto cycle depends largely on the compression ratio, which is the ratio of the maximum to the minimum volume in the cylinder. A higher compression ratio generally leads to better efficiency because it increases the temperature and pressure before combustion, extracting more energy from each fuel cycle. However, if the compression ratio is too high, it may lead to knocking, where the air fuel mixture combines prematurely, potentially damage to the engine. Thank you.